Welcome everyone for High Performance Computing, our lecture 6, second part. And this is about accelerators and graphical processing units. So in the first part, we revealed a little bit the difference again between multi-core and many-core, and then we quickly were going to real concrete implementations. And this was good in this lecture because then we really realized that basically a GPU in the end tells you nothing. You have to know a bit more, right? So many core, okay, I know with a GPU, but we have learned that it depends now how the cores are created. We learned a little bit about tensor cores versus normal cores. We learned that many of these systems are vendor specific. So NVIDIA is here a big name to say, with CUDA as one of the programming model for this. And there were different architectures that over time deliver more and more performance. There was Kepler, then we came up to Volta, then Ampere, and then nowadays we have even Grace Hopper. So this is a very fast pace of evolution of these accelerators. And also what we will look into again a little bit is now in the second part, how we program all of that, which is in one respect very similar to all of them. Of course, you have different software packages. For instance, again, CUDA for NVIDIA, but for AMD cards, you have another package. And the still bottleneck we observed are the things that there's always this host CPU in a way, right? So that means we always need to load data to the host CPU, upload data to the device memory, then do our kernel on the GPU, and then download the data again. And this is, of course, one of the key bottlenecks where many activities face to improve that. Another element was the precision. So you have seen that from 32 double precision, then we came back to 16. So in a way, some of this has also to do with precision. And we see that more and more of these cards will be getting towards deep learning, AI workloads. And this is something also I want to address here now in the second part. So we look much more into what are the existing libraries for computing. Do I really have to implement really from CUDA, from scratch, every little software package? Or are there not provided GPU libraries? What is a programming model from an abstract point of view? Again, thinking about the data, where I upload the kernel and so on. And then we will also discuss a little bit about standardization in the end. So when we have these different vendors, isn't there a chance or let's say a view that standardization is needed in programming, similar like MPI has done before for shared for distributed memory, or OpenMP for shared memory. So think about many core systems. We have done this example. Again, it lives from the fact that we have a very high throughput of very small tasks. So the normal CPUs, you would say, have high single thread performance. The GPUs have just moderate performance here, but this moderate performance we have seen then also in part 1 was then equipped with lots of these cores, or CUDA cores, for example, in the NVIDIA ones. Hence, it enables us to have relatively simple computing, but in a massive scalability and parallelism. And if you think about what we learned in the matrix vector multiplication as an example, you see that as a color code here. Again, it's very simple computation, right? It just maybe if you can think about now that the matrix is really huge, lots of smaller computations, but very many of them. So they're not so computation intensive, but you need just a lot of them. And this is beautiful to parallelize basically on these GPUs. And the most impact where GPUs have had a kind of success story was really this deep learning aspect. So AI, artificial intelligence, deep learning is one part of it. Hence, our lecture 7 will also talk much more about deep learning. So I will here just make the connection. And then, as I said earlier, in lecture 7, we will dive and start diving really into applications in the course. So deep learning will be one of it, AI workloads, where then really GPUs have a massive advantage. And in one respect, you could even say it was vice versa. So given the rise of deep learning, more and more GPU power was required, and more users use deep learning for AI workloads. Same is true with large language models. So this AI elements were really also partly a driver of the evolution of the GPUs, while on the other hand, deep learning is basically just enabled by GPUs, because you will see if you take the final project around deep learning that you cannot really use CPUs for deep learning that it makes sense. So only in very exceptional cases, usually you see the speed up is so low that you really need for deep learning GPUs. And this was a perfect conditions, of course, for accelerators to find also an application area with a massive growing amount of users. So again, just for deep learning briefly and to understand it what it is, we have a small video here. So here I would like to end because it makes an interesting point here in the video. So in the earlier elements of perceptron, the multi-layer perceptron, you have seen these connections, and each of these connections stands for weights of certain neurons that you have to learn, which represent, so to speak, the learning in a big network. So perceptron is a very simple learning model, not many parameters to learn. Then you have seen more artificial neural networks, which looks like this a little bit here on the bottom left. You see that you have some input layers and you have seen some other layers. And then, you know, the output was in the character recognition here from 0 till 9. However, now the move to deep learning, you see different things. That's why I also have here this kind of interesting showstopper and say, when you think about deep learning, it doesn't mean necessarily it's just only neurons and more hidden layers, hidden layers, hidden layers, and so on that we are used to have, let's say 20 years ago. Now we're talking about neural network architectures and deep learning architectures, which are very sophisticated. And they have lots of different elements. One of it, and of course in lecture 7, we will reveal much more. One of the interesting elements here of the convolutional networks that you see in the video nicely is to have this kind of feature maps and to carve out in a process we call feature extraction, really the kind of the features that you have in this particular image in order to recognize it as 3, as 9, as 0. So this is a step, this automated feature extraction, which wasn't there, let's say 20 years ago. It was there, but we couldn't do the computing. In other words, we see here an architecture which is very different from the traditional, you know, artificial neural networks with 2 hidden layers, but rather have a sophisticated way of really carving out features still in a layered way. So you see we have some convolutional operation sampling, and then another convolutional operation sampling, and so on. This is more like of higher level view that leads us then to this feature maps that you see a little bit here also recognize a 9 in different, very many ways. But this enables deep learning quite a sophisticated performance, not 100%, because there will be always these fellows which are not really learnable, that even humans would have a problem with to understand, is that 1 or 3 and so on. So still we can say that deep learning, to come back to our accelerators, again, deep learning will be also more explained in lecture 7, but we can really say that, you know, GPUs were enabling deep learning because each of these different layers that you see is comparable to matrix multiplication, matrix vector multiplication we already have seen. And this is beautifully supported in GPUs, which was one driver of success in this area on the architecture layer, which I also discussed in the part 1, the tensor cores, which are now come along that maybe don't have the biggest precision. But in deep learning, you sometimes also, given the greatness of the architectures, a large architecture, and also a sort of regularizing effect, it's not really so much needed, because you anyway don't want to learn any data point by heart, but rather the patterns that lies beyond it. Almost that you have seen a little bit in the feature maps. That's what you rather want to learn. But the other success really that was, again, in two ways, basically enabled by GPUs is really the TensorFlow Keras, for example, software stacks. There's these days also PyTorch, very heavy used, where you have exactly also open source packages available to leverage GPUs. They have an implementation also to work with CUDA, so with the NVIDIA way of programming it, and are beautifully supporting then the GPU computation. You see, you can also run it on CPUs here from the worker, but again, there will be a big problem that usually big deep learning architectures today will be very, very slow. You don't want to do this. Keras is a more higher level API and Python package, which is now basically also inherent in the TensorFlow 2 package when you download it. It is sometimes a bit more easier to program because it has a more layered way of thinking than rather the pure tensors, which are nothing else than multi-dimensional arrays. So this is something where GPUs are also then supported on a higher level, meaning again, more data scientists, which are not so inclined with the low-level GPU details, or not even, think about the mapping of the GPUs to these particular elements, could just simply use it. So this is a big success in both directions. Of course, now that more data scientists can use it in all different domains, this GPU technology, obviously there's an increasing demand. And this gives the vendor, of course, money, gives the vendor also the motivation to carry out more research to get better GPUs over time, as we have seen from Kepler, Pascal, Volta, Ampere, and then also finally now this Grace Hopper architectures. Here's an example of a real life application work that is coming out of my research group. For example, we are using deep learning at scale. So not only one GPU, but very, very many together in one application. And here in remote sensing, we are observing essentially, firstly with satellites, the surface of the Earth. You see that here a little bit. And many of these data sets are actually open source. And then analyzing with this satellite data now the land cover. And for this, we use deep learning or artificial intelligence more broadly. In previous times, we used something like support vector machines, random forests, and so on. But nowadays, deep learning has surpassed the performance of most of all the traditional algorithms if you have enough data, right? So this is now one big if, because deep learning in a way not only needs GPUs, it also needs to fill the GPUs with lots of data. If you don't have lots of data, chances are that support vector machines and random forests do a better job. But here you see we have quite many pictures available of this data set, for example. And this is one example where you then have an architecture that is much more deeper and much more complex than the one you have seen in the video, right? Which was about the character recognition from 0 to 9. So here we're talking about the residual network 50 architecture, sort of a de facto standard here and there for image recognition tasks. And you see here the input as an image coming in. It will be then in many steps again and again coming through different layers in this convolutional processes. Some smaller elements are not shown, like sampling and so on. And in this is now the point that these are very simple operations in a way to train it. It's just extremely many of it. And to give an indicator how many is best reflected in the trainable parameters. So every of these connections are more or less trainable parameters. You don't know them and you want to recognize them and learn them. So in the ResNet architecture, you would have around 25.6 millions of trainable parameters. And they are trained again and again with sort of backpropagation and elements which I cannot go to the very deep details in, but they do it over and over again, going through the network, learning from the errors, backpropagate the error, and again test it, then backpropagate the error. In other ways, you would say you're always thinking about of improving these many connections, which are around 25.6 million. Hence, many operations of this are actually not so computationally expensive. Again, it's the GPU that then has with many cores the opportunity to have the simple operations nicely supported in parallel. As we do here with remote sensing datasets, and also in lecture 7, we will talk a little bit about it. Now, there's one thing we have not touched yet also in more detail, and I want to bring that on the table for you. This is the multi-GPU usage. I was often, referring to the fact that our team or many other researchers that use HPC don't use one GPU. They use, in fact, multi-GPUs, all in parallel for the same application. So this is really what brings us into HPC, and this brings us to the point why NVLink, what you had in the first part, for instance, and this network interconnectivity we learned in part 1 is also incredibly important. So we see here one example, again, from this application example we had, where we have the execution time and then the number of nodes, right? So a bit simplified, by increasing the number of nodes, you have here 4, 8, 16, 42. This is something where we have 24 nodes used with 4 GPUs each, right? There's a 4 GPUs per node in the Jewels booster. So we use that with basically supporting the application with 96 GPUs in parallel. So you fill them with data, you have enough data, and then you're basically fine to go. However, what we didn't discuss is how you now enable this on the software front. And this is something where different software packages, again, are able to help. One is here Horowot, another one is PyTorch GDP. But I will make the case here of Horowot also because it nicely links to some things you already know, which is MPI. So how this works is essentially abstractly shown here. You have your data and you have to fill the data to all the different processes that you have on all these different nodes with the GPUs. And what you do is you have a different model, and then you basically compute the gradients. You update the gradients, you sort of learn from this. So it's a bit hard to understand completely if you don't have learned deep learning. We go into this a little bit more in lecture 7. But the learning process essentially means we learn from the data at hand of our model, which is not the whole data, right? We now basically have distributed this across many nodes as we learned here. But in the end, we learn from this partly from this data that we have, update our model and say, okay, we did some errors. What would we dare to do here? But then in order to update the model, we don't keep our own learning progress for us as a GPU node, or basically as a node with many GPUs. Here we want to do then the average gradient exchange, right? So that means distributed training in this area, where before I have the averaged gradients updated my model, I need, of course, to do the average now from all the different gradients on all the different nodes. Hence, communication is needed. And you know already what happens when we talk about, multi-node communication. This is the MPI standard, right? So here we use an MPI or reduce. Reduce would be, one way. Or reduce means everybody gets the reduction operation outcome, which in our case is now having an average of the gradients that you can then per node, update the model. And in this sense, you have a distributed learning possible. You need the high throughput really in each GPUs here per node to compute the gradients, to do the learning progress via backpropagation. But you need also the communication between the nodes to average the gradients to get this basically across all the different nodes. And of course, there could be also scalability issues if you think about that the systems are bigger and bigger. In this application example, we maybe could have used up to 56 compute nodes, where each of them had four NVIDIA cards, for example. So with this, there are essentially theoretically not directly limits, right? So the only limits are then data. Do I have enough data to use more and more nodes? it doesn't make sense to use more and more nodes if I cannot fill the GPU with data. And on the other end of the scale, you would say, maybe it is also, not really giving us an update of the learning progress anymore, but rather gets away the accuracy. So just parallelization for the sake of parallelization is also not good. What do I mean by this? Is something like overfitting, or you have something where, we parallelize, but the kind of accuracy goes down, like in other systems and other approaches sometimes in this area. So this distributed training is loaded, and it's a matter of huge research, and is now basically also supported in many, many different packages. And again, when we think about, leaving a little bit, not only the focus of AI deep learning, you see here that the CUDA implementations and all the different application packages become more and more broadly available. So you see here quite many areas. Scientific computing stands for this kind of simulation sciences, really, data analytics, deep learning we just looked at, but also in many different fields, genomics and so on. There are now CUDA implementations of existing packages which are available. And I showed you here a few which are really very well known in the field. Ember, for instance, GROMACS has been around, and NumD for a long time, enabling us molecular dynamics. Basically, if you then go to physics, you have different packages, and also to geoscience and also engineering. So here you see really with this kind of GPU enabling, also all these, application packages get a speed up. And the beautiful thing is, you, as a user, maybe using Ember and GROMACS for many years, your way of working with this particular software library is not working very much differently. It just leverages now the GPUs more than it did before. And that's something which is another key success of this, including those that you have learned from the AI and TensorFlow deep learning. So in a way, people have done these things before, but they don't need to shift a lot just because there's now more GPUs available or different types of GPUs available. So this helps a lot. Also the uptake of these GPUs, it helps to give the vendors, of course, more demand for GPUs, because more and more scientists, more engineering disciplines really require it. And this is a quite good driver of this. And here again, for comparison, a couple of these packages which are very much known, and also show you the number of it. 450 plus GPU accelerated applications. Note, of course, they are accelerated for NVIDIA, so very specific architectures around our NVIDIA vendor, but many of those soon and also in the future are probably moving to also adoption of AMD and other tool sets. So examples include, again, maybe Ember, which you basically not know very much about, but molecular dynamics field, but you know already about OpenFOAM, right? Of course, also this is nowadays also possible to use GPUs with. You have GROMACS as another, and NumD as another idea of doing molecular dynamics, but you have also ANSYS Fluent, for instance, which is another CFD and engineering package, which also Reza will talk in successive and in subsequent lectures a bit more about it. And also these packages are nowadays GPU accelerated. Here is WAF, Weather Research and Forecast, is another code which is actually GPU enabled. Just to understand again also, because many students asked me in the past, so are we talking about just having much more gamer cards inside? This is not the case, right? You see here basically that NVIDIA has many different lines. So you have the GeForce cards that many of you know from gaming and so on. But we're talking here about the Tesla lines, which are much more optimized for high performance computing. So yes, in the general principle of the GPU remains across all of them, but we're talking about very specific developments of these chips for different purposes in these different production lines, right? So and this is an important part to understand. Another crucial part is, again, something I was talking about a lot in the last couple of lectures on a relatively abstract level. I was always saying, like, well, one of the benefits of GPUs is throughput, that's fine. But one of the limitations is you have always a host CPU you go through, right? So, and I want to show you a little bit with steps here, derived from a GPU course that we have at JC. Another example of that, you have GPU courses for several days, right? Which I transferred to you here in one lecture only. So bear with me. So that you at least get a little bit the general idea how you work with GPUs. And this is again now a little bit abstract from exact the architecture you use. This is the V100, Hopper architecture. We have areas to go this way from CPU to GPU. So let's go stepwise through this. So you have the host CPU on the left side, as I was always having abstractly shown. Now we go into a bit more detail because it's needed that we differentiate CPU between CPU and CPU memory. The same is true for the accelerator here. It would have a scheduler scheduling all the many tasks around it. It has an interconnect, of course, to actually connect, and some device memory, we would call it, and some caches. But the device memory would be, of course, very crucial in order to get data somehow loaded. So in step one, what you would do is essentially take data that you have on the host CPUs and transfer this data from the CPU memory to the device memory, right? Device is a more general term because some people, GPUs is one term for it, accelerator is another term. That's why some people say it as an acceleration device more generally. And in the future, we can see even maybe other chips as being acceleration devices. For instance, we do some elements with quantum annealing, quantum computing, which is also not general purpose computing, but could be very good, for instance, in optimization. So you would have quantum as another sort of specific GPU-like device that accelerates the optimization for very specific purposes. However, coming back to the GPUs, now with the, basically data of the concern in this particular GPU in the device memory, we now have actually also to do something to compute, right? So in other words, what are the tasks you want to execute on this many cores? That is something that we call the kernel that is operating all the many core things. In other words, the instructions that you have to work on this particular data. And this is already very, sort of vendor specific. So here we would talk, for instance, about a CUDA kernel that is implemented in that for CUDA, in other words, NVIDIA GPUs. But think about that this is, of course, some instruction set coming from the CPU to tell the scheduler, you should do now a matrix vector multiplication with the data you have in memory. Obviously, this needs to be programmed, which data structures and so on, but that is a general modus operandi. Then, of course, the scheduler of the GPU has to do something, and now allocating all the different, many cores, but also get data, or in ideal cases, also cache data from memory, and of course, write results back, which is also important. Again, we have this just then here as the whole interactions between the devices, and within the device and not between the devices. So hence we have to also think about that this is now just within one GPU, right? So the process is very similar per each GPU, but if you do multi-core, multi-GPU training, then of course we have to add another level of complexity. But here we talk about one GPU. And when we have done this, of course, in the end, we want to have somehow the results back to the host memory, right? And now it starts what happens, as I told you, when we think about averaging the gradients. There needs to be more logic to involve Horowat, right? To average the gradients and then update essentially the elements. This is not really covered here in the GPUs. However, this is now adopted in many different applications. You see here one very famous one. Some people have probably heard already about the BLAS, basically linear algebra subroutines. There are around 150 of those, and they're always used for linear algebra in all sorts of scientific applications. Here I have this XPy that is basically there, which stands for, a shortcut for single precision, 8 times x plus y. So you see that a little bit here, 8 times x plus y. That's where XPy stands for, and S is single precision. And this is used in many different scientific applications for many different purposes. And the typical way of implementing this in a CPU would be you have an operation for it. You get some, of course, parameters with it. what is A, X, and so on, and Y, and so on. So, and then you would basically go through this array, right, or the vector here shown there, and do this iteratively. And of course, the cuBLAS library now should enable us to have not really the necessity here for doing a loop, but rather solving the loop completely as a GPU, as we have already talked similar like with OpenMP, right? There was a very similar element where we said like this can be nicely parallelized, because here all what we do is we multiply with a constant and have then another vector added. So this is independent from other runs, so it's quite nicely parallelizable, because here the index, as you see in the CPU version nicely, is always E. So this is a good example, again, for parallelization, a very easy example to follow. So obviously there are other routines, and they're all parallelized and available, especially in the CUDA BLAS routine. But how it works then when you use it in CUDA looks, of course, a little bit different than you would have just, your CPU version, the sexpy loaded. And you see that here's a couple of examples where you have to initialize, of course, elements of the device. Then you would allocate GPU memory, right? So this is, of course, now something which is an important part of it, because we sort of sending, again, almost like MPI did, we're sending now the data from the host CPU to the device GPU. That means there needs to be space for it. So in the device memory, we allocate the memory now for our X and Y. And then, of course, we copy the data at some point in time to the GPU. Still, of course, this is a little bit, abstracted, so you don't really have, low-level commands. It's still a good API that you can use here to set a vector, for instance, that we have just seen, and so on. And then call the BLAS routine that we have, which is CUDA aware with the concrete parameters. Based on that, what I already allocated, that should be not a problem. And then, of course, I get the results at some point in time back, right? So this is also nice. And now I have the vector, which is the outcome now of this, routine from this sexpy back on the host CPU. And then I can work on the host CPU for different reasons. I can think about changing elements in my scientific applications, whatever I needed to use this BLAS routine for. And then at the end, finalizing to give some, handle free. So this is the way how it roughly works with the GPUs, with example of using, for instance, very specific implementations for NVIDIA cards. So the CUDA, as I was evolving to, and the implementation that we have now in the cuBLAS. Now, more generally speaking, we think about always standards in this community, because we want to port applications between different HPC systems. We want to make it easier for the application domain scientists, right? Think about medicine people that want to work with this and then have to program very much low-level elements. So more and more we come to simplifications. And one of the ideas is now also to think about that, of course, existing libraries should support GPUs much more. You know that a little bit from our previous lecture, lecture 5, where we had then the Pragma OMP already, the shared memory, and where we can do elements with loops here. This was, it was really a little bit similar like we have done with the accelerator, right? So for instance, parallelization of a loop is relatively straightforward, especially as we have seen in sexpy that the indices don't matter so much. Now, what have people started is to have a Pragma ACK essentially here, an addition to this Pragma statements with accelerators, where you have a parallel loop construct, which does essentially similar things like we had in OpenMP. Remember the master thread always lives and joins and forks and joins later than all of this parallel region here. In a similar way, you can see this is working in OpenACK as well. So an extension of the OpenMP, if you will. But instead of using this now with parallel threads on your CPU, you use a device, basically the many-core GPU with many of these parallel many cores. So in a way, a relatively straightforward step, which is now supported by OpenMP as well. And by having this, here's another example. You would have then the opportunity again to do this here with the OpenX standard, to do this hexpy, for instance. So when you have already a C code, for instance, and an operation that you have here, we had discussed for the CPU, you can now quickly instrument and add the, let's say, Pragma Sentinel here with ACK parallel loop, copy, of course, the Y and copy in the X that you need here for the computation of this, you know, of the sexpy in the end itself, and then it will be automatically computed on the GPU device. Here you see this a little bit differentiated from the device. So the waiting for code is the GPU is idle if you want. If you start the main operation, at some point in time, the host CPU will transfer then the code given this, and the kernel will be running here and finish the code, and then you will bring the data back to the host CPU. So there are kind of small transfers then that are there, but they also observe that in a way the host CPU stays idle, which is another disadvantage. Or in other words, what you sometimes do is, like in the Jülich booster architecture, you would say, if you have cutting edge GPUs that do a lot of work on these, maybe the host CPU doesn't have to be so strong because it's many times not really much used. More recently, also some people try to do both in parallel use. So maybe preparing some data sets to be uploaded again in the next iteration. So to also keep the CPU not idle, which of course is bad for us in a way. We always want to utilize the resources we have. So different elements that can influence also now the performance, which are previously not there. And in the future, it will be getting more complex. I think that's what we already observe today. My team and other teams have already access to AMD cards, here, for instance, in Lumi. And you see that AMD is now basically one of the competitors of NVIDIA and has two systems here also in the top 500. One of them we know, the Lumi system, where iStand is part of, which is also a modular system. Interestingly enough, if you look a little bit around here, you will find still the computing partition with really cutting edge computing, but also a GPU partition, which is in our case the booster partition in the Joule system, for instance, and then one for data analytics partition and so on, and another accelerator in the future, maybe for quantum elements. But long story is to take away, we need the GPUs to proceed. We will see the rise of NVIDIA probably more and more, but also given the competitors now, for instance, with AMD Instincts, you see that the first exascale system in the world was a basically system which uses the AMD Instinct cards here. So there's also some change to happen. And with this, there's really a question of what we can do with standards, how we can improve the situation for application domain scientists to think a much more way of getting away just from pure CUDA, getting away maybe from the AMT rock toolkits, getting to a much more streamlined way how you do it. And there are some activities and initiates on the way, which is here, for instance, the HIP, so to speak, not standard yet, but you would say it's one of the ideas of how you can combine, for instance, CUDA and other cards coming from AMD, for instance, with some code which should be executable on all of them. You have to have then some, terminologies to be a bit more generalized. If you think about CUDA, when you have a thread or warp and elements that, are sort of related to how you process data, how you work on the many core GPU, you would have in HIP a couple of different elements, but the concepts of it would be very similar. And with this, of course, we can see it is still similar probably what we do now in CUDA or in others, especially as CUDA has quite a long footprint now in applications, right? So we know how to handle it. Still, there are chances that this HIP interface, for instance, will be then also working with AMD and many other vendors, maybe from Intel, for instance, in the future. And you see here one example, HIP versus CUDA, which tries to be quite, let's say, vendor agnostic, so not really thinking about this vendors and the bottom, but still see that many things are very similar. We still have to allocate, right, in the device some memory. then we have to still have the bottleneck, no matter which standard we use, to copy the data we have from the host CPU to the device memory. Then we have some sort of kernel, some optimization, some computing we want to do really, which is here very similar, of course, to be done in HIP like we did in CUDA. And then you have the CUDA memory out again. So of course you want to get the results back to your host CPU after that. And then you see, of course, a major step, and that's the idea I wanted to convey to you, will remain the same unless we get more technology breakthroughs, that maybe a CPU is much more easier to get data to an accelerator. So, and that's basically concluding also the different viewpoints in the end, where we are heading to. Obviously, for HIP, again, you can do a workshop over several days, for OpenEgg as well. So my lecture here is really just scratching the surface again in favor of getting much more to applications. So what we have essentially in the next couple of lectures to come is really a set of applications rather than technology. From a technology point of view, and maybe also by finishing up by this movie, it's a quite nice view also that different vendors play now in the game. What is interesting for you is that you have learned the basic principle of HPC technologies now. So we reached the peak, if you want, a little bit in the course, that from now on we will reuse that technology. So not introduction of new technologies, but rather thinking about really how we use them in different applications. As this course is really primarily for CFD, lots of CFD applications will be coming in the next part. But before we go there, we will learn a little bit about the applications from AI in remote sensing and others in lecture 7. So see you next time.